So if we are going to take this idea of proofs one step further, we want to prove things with generic cases. So we're proving them for all possible examples, and we have to do that with variables. We can't use specific coordinates. So naming as specifically as possible means that we need to look at side length, because that's how we name triangles. And so we are going to be looking at potentially a scalene triangle, no equal sides, an isosceles triangle, 2 equal sides, or an equilateral, all 3 sides are equal. And the only way to determine side length is to look at the distance formula. So let's start here with A to B. So I'm going to also be very careful and very clear with my work. And I'm going to say the distance of AB is equal to, the order doesn't really matter, but it's a little cleaner if you take B minus A. So I'm going to say A minus 0, the quantity squared, plus B minus 0, the quantity squared. That simplifies to A squared plus B squared. That is all the more that it simplifies down. I cannot take the square root across an addition subtraction, and so I'm done. So now I'm going to go ahead and I'm going to figure out the distance from A to C. And so when I figure that distance, I have the distance of A to C. So again, I'm very clear with my notation. I'm going to take the distance of 2A minus 0, the quantity squared, plus 0 minus 0, the quantity squared. And so that is the square root of 2A squared plus 0, which equals the square root of 4A squared, which simplifies to 2A, because I can take the square root across to multiplication. So now I need to go ahead and figure out what is that distance of B to C. Now, again, the order doesn't really matter, but it's a little cleaner if I take C minus B. And so I have the square root of 2A minus A, the quantity squared, plus 0 minus B, the quantity squared, which is equal to A squared plus minus B squared. It's going to be B squared. So what I have when I compare this is AB and BC are the same. This one is different. And so what I can conclude is, therefore, triangle ABC is isosceles because AB is equal to BC. By definition, isosceles triangle. And your work and the explanation is what constitutes your proof. So just to add a couple more ideas to your understanding of geometry and triangles, is there are specific angle-side relationships in triangles that become very useful, more common sense on how to set these up, of knowing your answers are right or wrong, and just understanding how triangles are built. And the first one says, if one side of a triangle is longer than another side, then, so here's our if-then situation, the opposite angle opposite the longer side has a greater measure than the angle opposite the short side. Translation, little side, little angle. So we can actually order our sides and angles based on their size. So the littlest side will always be opposite the littlest angle, biggest side opposite the biggest angle. So we can make some conclusions about sides and angles based on lengths of the others, and we can use that to check and have it kind of as a common sense if our answer is right. If our answer comes out too big or too small based on the relationships, we know that it's not right and need to go back. Part B here says if one angle has a greater measure than another, then the side opposite the greater angle is longer. It's the converse. Okay, little angle, little side. And so we can go through and order our sides and angles. So if we are going to do just that, order the sides of ABC from smallest to greatest, we're missing one angle here. We're missing this angle. So 180 minus 95, which is the sum of the other two. Triangle sum, all three angles are 180. And so we end up with 85 degrees. And so smallest angle, smallest side. Now, just as a note, we name sides with lowercase letters of the angle opposite. So this side is either side AC or little b. This side over here is little c. This side is here is little a. So from smallest to greatest, we have b is less than c is less than a. Because a is opposite the biggest angle, that makes it the biggest side. Order the angles, obviously from, sorry about that, from smallest to largest, smallest side, smallest angle. So angle C is the smallest, that's less than 5's in the middle, it's opposite B, angle B, which is less than biggest side, biggest angle, angle A. So again, an interesting study in how they're related. It should make sense that a smaller angle is going to connect to a smaller side opposite it, but it's really nice if you're solving for sides and angles to think about what range of values would be appropriate, which brings us to our last point today, triangle inequality theorem. There's a relationship between the sides of any given triangle. And what it is that the sum of two sides, any two, must be greater than the third. If it's not, the triangle doesn't exist. And notice it's greater, not equal. So for example, 2, 3, and 5. And I always like to draw pictures. 2, 3, 5. So what I have to test is 2 plus 3, is that greater than 5? Is 3 plus 5 greater than 2? And is 5 plus 2 greater than 3? I must test all of them. They must all be true. Well, clearly, right here, this is false, not a triangle, because 5 is not greater than 5. It's equal, not greater. So you run through the next, 5, 7, and 9. So 5 plus 7, is that greater than 9? True. 7 plus 9, is that greater than 5? Yes. 9 plus 5, is that greater than 7? Yes. Therefore, it does make a triangle. This is also a useful theorem, a useful property, if we want to find a range of values for S. So let's say we're building a flower garden or we're building a fence. There's a range of values of where this S, it could be this big, it could be this big, it could be somewhere in between. But it will only connect to make a triangle if we are within certain values. So if I go ahead and set up those three relationships, and so I would set up that 4 plus S must be greater than 7, S plus 7 must be greater than 4, and 4 plus 7 must be greater than S. If I solve them, subtract 4, S must be greater than 3. Here, S must be greater than negative 3. And here, 11 is greater than S. Well, clearly, that's a nonsense answer given a real context. These two tell me that the smallest S can be and the largest S can be. So somewhere between 3.001 and 10.999 would be potential values for that last side. So that ends the additional information for section 4. Good luck on your homework.